4.8, kinetic friction. Friction and kinetic friction. The intro to friction and mainly specify kinetic in this one. And of course, these symbols you've seen: normal force, friction force, and this weird one, mu. Mu is back, but mu this time doesn't mean micrometer. Mu with a K. Work number 1 and number 3, and if you really want to, you could try 4, but I think 1 and 3 will be fine. Now, this some of this gets into some craziness and you'll see as we move on. I'm going to read the first part of the notes here. Whenever an object slides across a surface, a friction force exists between the object and the surface. And I was showing you this in the other video, just saying, like, here's a surface. If it slides across, there is a friction force that is slowing it down. Now, of course, if you have a real slick surface like this one, or you oiled it really well and had this oiled as well, there would be almost no friction. It'd be very, very light. And when a ball bearing like this rolls down, oh my goodness, I didn't want to hit that. Okay. Well, anyway, when it rolls, you can almost ignore friction. It's almost supposed to be like, you know, friction can almost be ignored completely with that, something like that. Almost. I mean, if there were no friction on a floor, you could roll an object like a bowling ball. In fact, think about that. You go to the bowling alley, back when you went to bowling alleys, or if you're able to, when people were able to go there, they'll have it waxed really, really slick on the lane that you're bowling into. And when you bowl that ball, you know, even if like somebody gets up there, the smallest little child just starting the first time to bowl, most likely if they roll that ball, it's going to go all the way down. Now, it might go into the gutter, okay, but it's going to go all the way down. It might be real slow, but it's not going to stop. Whatever speed they started with, they're going to get there. Now, they can stop. You know, if you go really slow and you see a bowling ball stop, it's kind of rare, because the point is, you can just, if you throw it with any kind of a little bit, you know, minimal speed, that ball will go all the way down that lane, all the way to the end, without you having to do anything. And the speed at the end will pretty much equal the same speed that it had right when it hit the floor. So like Newton's law, that it will continue in a straight line, the same direction, as long as no force acts on it. Well, the friction force is almost non-existent in that. You can make the bowling lane double long, and for most people, and then you rolled it, and it's going to go the whole way. So, I mean, it's not perfect. I mean, like I said, some people try to find the best way they can try to make it stop. But anyway, all right, that's not the goal of the game, though. All right, the force of friction exists in two situations. When an object is in motion, we call that sliding friction or kinetic friction. When an object is at rest, we'll talk about in the next part, it's called static friction. So there's static friction, and then there is sliding friction. And as we talked about, or as I mentioned before, I mentioned this before already. Well, I'll get it in the next lesson, though. But if an object is already in motion, it's easier to keep that object in motion. You need less force to keep it in motion than when you take an object and you just want to start it in motion. Like, say you have like a shopping cart, you know, Costco or somewhere, and you got full, is really, really heavy with a lot of stuff. You go, oh, I just can't push this. Or Home Depot would be better, because that's when you might put heavy materials in it. I don't know if y'all go through anyway, get stuff. But if you had a really heavy cart, it's really hard to start it moving, okay? Like the force needed to get that thing moving, it takes a lot of force. That's called static friction, the friction you need to overcome to get something in motion. But once it rolls, once it's moving already, as long as you keep walking, it's not that hard. You can keep a lower force. So static friction takes a big force to overcome, but then when you're just moving along, kinetic friction is a lower amount of force. All right, number 2, the bottom part, important points about friction. Number 1, friction force always acts in the direction opposite of the direction of motion. That's important. So when you're friction on a surface, you know, whatever it is, this box is being pushed along on this surface right now, friction will always be, just say I'm pushing it, whatever. Friction force, a lot of times we'll draw it down here at the bottom, and we'll put FR. It's going to be opposite in the direction of motion. That makes sense. Friction is not helping it speed up. It's going to try to slow it down. Number 2, the magnitude does not depend on the speed of the object. So it doesn't matter how fast you're going, the friction force will be the same thing, okay? The only thing that it will change by, it will be dependent on, is dependent only on number 3, it says there, only on the normal force. It's how strongly these two things are being pushed together. And I can show you that, like, first of all, if I want to push it along the surface, like it is right now, the friction's the same if I'm pushing a heavy box down a hallway, okay? Just say, like, if you're at school in the hallway, the hard floor, if you had to push a really heavy box, you could do it down the hallway. Just say every time you push it, then you let go and it just immediately stops. So you have to put all your force to push that thing to overcome friction the whole way. You keep going all the way down. Well, what if what if a friend of yours came along and said, "Oh, okay," you think, "Oh, they're going to help me." No, instead they sat down on the box. Okay, I'll put a little on sat down on the box. Is it going to be easier or harder to push it? Think about it. The friction is the floor didn't change. The friction does not change. Actually, you might think it, but it doesn't. Well, I won't say that. The friction force is going to be is going to change. It's going to be changed because of normal force. Because she is heavy, she's adding more weight on this. She's pushing the box closer to the ground. In fact, I better just show you this right now. You bet, what in the world? That's the equation for friction. Friction is equal to the normal force. So remember, the normal force is the force pushing between the two objects. You have the weight pushing it down. Then you have the normal force pushing up between the two surfaces. The force that's pushing the floor and the box in contact. That's the normal force. So friction depends on the normal force. How much are they being squeezed together? And that makes sense. When there's no girl was sitting on the box, it's hard enough to push it down the hallway. But now the girl's sitting on the box, it's hard to push it because her weight, she's causing it to be more in contact with the floor, and that means she's increasing the normal force. Think about that. She actually doesn't increase the weight of the box. She's sitting on the box. The box has the same weight, but now we have to add her weight to it. In order to get the normal force, we got to add her weight. So the normal force will equal the weight of the box and her weight as well. So that's why there'll be more friction. But I'll just say anyway, that's how you calculate it. Now another way to think about it, like for chemistry, microscopically, there is no smooth surface. Even the floor under a microscope would look like jagged. We'll just say imagine like jagged edges. And also the box itself, if it's a cardboard box or whatever, but it would not be perfect either. I'll make it a little bit different. I'll make it a little bit more, we'll say it's more smooth. Well, you can see, if I had to push a jagged edge against a jagged edge of that, you'd be like, now you can see where friction comes from. But again, it's more like at the atom level or maybe microscopic level. You couldn't really see that. So there are no smooth. If there were completely smooth surfaces, or you completely oiled down like a lane here, and the bottom of the box was completely oiled down, you could push her one time and let go, and she'd slide all the way down. There'll be zero friction. Okay. Okay, so there's my little explanation, and there's the friction force equation. All right. So let's try. Oh, there's a picture in here of Leonardo da Vinci, one of the first scientists to study friction, found in his journals, but he never published it. It said friction force between the object and the surface. Oh, it varies. Number 4, it varies with different objects and surfaces. As you know, if you want to push a brick across like a say LA Unified floor, a smooth, hard floor, a brick. Think about that. Well, think about pulling the brick across the concrete, like on the ground, asphalt, on the street. How about that? Or a sidewalk. It'd be harder on a sidewalk or street, easier on the LA Unified floor. What about if you had to take a brick and slide it across a bowling alley lane? Don't do that. The owners of the bowling alley are going to come at you, But obviously, it would be easy down a bowling alley lane, real slick, but it would really be hard across grass, even, or across whatever surface. So this is a constant. Mu k is called the constant of kinetic friction, and that number is going to be a number less than 1 that is going to be equal. It's going to be dependent on the two surfaces. So what about like your shoes? A lot of shoes, like tennis shoes, have rubber on the bottom of them. Rubber against asphalt is really, really a strong, good hold. You don't want your shoes to have friction as you walk. If you think about it, you want to be able to grip the ground there. Now, if you tried to run with your shoes on the bowling alley lane, I don't know if you've ever done that. If the ball does go and get stopped somewhere and you try to walk out there, you can slip bad. And again, I keep talking about the bowling alley, my experiences. I don't bowl a whole lot, but I used to, a long time ago, we used to take some students at Venice. We used to have a little bowling thing that we did. Okay, the whole club. All right, and I put some other scientists. I didn't remember. All right, let me move on to the next page and do it. First problem A. It says, a 10-kilogram chunk of iron was pushed across a steel plate with a force of 45 newtons. So I'm going to put 10 kilogram, 45 newton force. I'll just put F, whatever, okay? Then it says, what is the net force on the object? Okay. We might also want to find the acceleration. We'll get that too. I might want to add that in. So what's the net force on this object being pushed? Okay. So I need to figure out all the forces involved on that box. We have the push force. I'll put F. Let's put a little P for push. Then we have the weight force. Then we have the normal force. All right, and then that might be about it. So the weight force is pretty easy to get. 10 kilograms times 9.81 meter per second squared, 98.1 newtons. So that's your weight. What else? The normal force. In this case, the normal force will equal the weight because you see there's nothing else pushing it down into that pushes the surfaces together except for the weight. All right? So the normal force will be negative 98.1. Or I tell you what, if you really, let's just say the weight's negative 98.1. The normal force is 98.1. You know, one funny way to view this is we know there's a normal force. If there were not, then this box, this whatever block of steel, would be falling through the ground. So it pushes on the ground with 98.1 newtons down in that direction. The normal force has to be supporting it. If it were not, then it would fall through the ground. Okay. Now, I'll just make this one more quick little add-on because it'll come in a later chapter and a later problem. So we said the weight is the normal force is 98.1. All right. 98.1, think about that as a normal force. What if I were to put the little girl, or I would just put some weight up here that was not 98 newtons, but let's just say if it was 30 newton. Say I added a 30 newton weight on top of that. Well, what's going to happen? Well, if I add a 30 newton weight, it's going to be harder to move it across the floor. We talked about that, the gravity, because you didn't increase the weight of the box, the total weight, but you increase the total weight down. You increase the normal force will be greater. The normal force used to be 98.1. If I added 30 more, it'd be 9, 10, 11, 128.1. So doing anything at all to push down on the top is going to cause the normal force to increase unless the floor breaks. But we're not going to let that happen in these problems. Okay, so we got the weight, we got the normal force, we got this force pushing, and there's one more force, the new one for today, and I'll draw it with a yellow. The friction force. And actually it'll be all underneath that whole side. And it will act in that direction. So, the problem, they said calculate the net force. I probably should have said first calculate A, the normal force. B, calculate the friction force. I should have probably divided it out. But we're going to get there. The friction force is equal to what's called mu K times the normal force, Fn. Now, Mu K is given in this problem. It is 0.30. I forgot to write that down. So, 0.30. The normal force we calculated to be 98.1 newtons. So my friction force is going to be 30 times 98.1. Where did I put my... Oh, here it is. Calculated. 98.1 times 30. 0.30. I'm sorry. 0.30 times 98.1. It's 29.4. Or just 29. Because of it's 2 6 fixed altitude 29. 29 newtons is your friction force. So A, the weight, we found that to be, I could have had 4 things. A, what is the normal force? Well, the weight force is this. So the normal force is also that. I could have called that B. Then B would have been, well, A, what's the normal force? Okay, we got the weight. Weight force. In this problem, the weight and normal force are the same. But keep in mind, you could see a problem where we add something on top, and it causes a greater, you got the weight of this, and you got this object, so your normal force will have to equal both of those. But that didn't happen in this problem. So first you might find the weight of the box. Then you find the normal force, in case you have to alter it from anything. But here they're the same. Then you find the friction force. Then the net force. Now, to find net force, let's remember, well, I can remember 98.1. It's right there. There's an equation that looks like this. And I kind of want to start using it because it's going to pop up in the next few lessons. The net force is the sum of all forces acting on an object, as many as you have, etc. But we're only going to be talking about one direction. We're not going to be talking about up and down. Well, in fact, how about this? The net force, if I do vertical, the net force will be the weight and the normal force. And since they're equal, negative 98.1, 98.1, they equal 0. It's not moving up and down, and that makes sense. So the net force in the vertical direction is 0. But now in the horizontal, what will be the net force? So vertically, there's no force. That would technically be part of the problem if we just said, what's the net force on it? Well, vertically, there's nothing. But now horizontally, there will be. And horizontally, you've got the 45 Newton force, and you got the friction force. That's all you've got. So the net force in this particular problem will equal, oh, by the way, you always put the vector, a little arrow. That just means, if you want to put parentheses too, what that would mean is I'm going to put positive or negative in for each one. So the net force on the box is equal to the force, the pushing force, I always call it the FP, plus the friction force. All right, you add those together. The net force will equal, the pushing force is 45 newtons, positive. You don't have to put a positive there, but if you want to, you could. 45 plus, and the friction force would have to be negative. So even though I calculate 29, it's negative 29 newtons. So 45 minus 29 is 16 newtons is the net force on the box. 16 newtons, straight ahead, this way, to the right, positive. Okay, if I ask you to calculate what's the acceleration of the box, I didn't put that in there. I threw that in because it might be on another problem. Well, bonus, whatever. AB, I call that ABC, the net force, and D, acceleration. Well, F equals ma. The net force on an object is the mass times acceleration. So if the net force is 16 newtons, it's equal to the mass, which is 10, times A. So 16 divided by 10, 1.6 meter per second squared equals acceleration. I want to bring up something here and just add this one bit in before I move on. Remember, if an object has a net force on it, then that object will accelerate, okay, if there's a net force. Now see, 45, this force and the friction force, if they were to cancel out each other, well, for one thing, the object wouldn't be moving, or it would stop very soon if it were moving. If that were 45 and that were 45, it would not be moving at all. If that's 45, negative 45, just like if the weight's negative 98, positive 98, negative 98, positive 98, positive 45, negative 45. If everything is 0, if the net force is 0, then, oh, I hate to say it won't be moving. It will not be accelerating. It will not be accelerating, okay? It'll be moving at a constant speed, or it will be still. It will be still. That's just something to think about. I'm going to come back to that later on. So if the net force on an object is 0, I hope I didn't say that. Maybe I did in the video. If the net force on an object is 0, that means the object is not accelerating. Doesn't mean it's not moving. It could be moving, but at a constant speed. Moving at a constant speed is not accelerating. Or it could be at rest, which is also constant, because at rest you're not moving at all, okay? All right. Okay, I wanted to throw that little bit in because I'm mainly thinking of what's going to be happening not on today's worksheet, but on some worksheets that are going to come really soon after when this stuff gets to be kind of crazy looking. All right? And we'll do one more problem. Oh, there's one more. Oh, no, I can do it with, well, I could have done one more thing on this problem that you might need to see. I'm trying to think about that. Maybe I'll do it on the next problem. I might just add something in to the beginning. Okay, it says a 12 kilogram rock, okay, 12 kilogram, 12.0, is pulled across a metal surface at a constant speed with a 59 Newton force. Calculate the coefficient of kinetic friction. Okay. You could say calculate. I should have broken this down again like the other one, but let's just say calculate A, the normal force, calculate the friction force, calculate the coefficient of kinetic friction. At the end of this problem, I might show you one more. I want to tell you one thing at the end of this problem. Maybe, I don't know. Yeah, I better tell you. Okay, I'm sorry. There we go. All right, it says it's pulled at a constant speed with a 59 Newton force. You know, I should have given you a diagram. I should have, or told you that what if you let it be horizontal? Or I should have put in the word horizontal. So will that be the force, pull, FP, can be push or pull in this case, and we'll say it's 59 newtons. Yeah, it's pulled at a constant speed at 59 newtons. Now, if you're pulling it at a constant speed, what that means is, well, the force you're pulling with, and look at the force that's opposing you, the friction force, guess what? They must be exactly equal to each other. If you're pulling at a constant speed, I mentioned that in the last problem, here it already is. So if you're pulling something at a constant speed, then you are, as you pull, you are basically fighting friction. You know, if you go touch it afterwards, it'd be like warm. So you are overcoming friction, exactly equaling out the friction if it goes at a constant speed. If it were accelerating against friction, then there'll be a net force on it. But there's no net force because you're pulling it at a constant speed against friction. So let's figure out what do they want you to find? Oh, they want you to find C, the kinetic friction coefficient. First of all, let's find the normal force. So we know we have the weight here. We also have the normal force, the opposite of the weight. And I'm going to show you in a minute something I could do to make the normal force not equal to the weight. I'll show you that at the end, just in case you had that problem, because I think it's going to pop up on one homework. All right, so friction force, weight force. Then what you do, so first weight, A. Weight is mg. This will be faster, I think, than the other problem was. So I was trying to tell you every detail. 12.0 times 9.81. So 12 times 9.81 is 118 newtons. So the weight, and we'll say negative 118 newtons. So therefore, the normal force equals 118 newtons positive. Now, the friction force. Okay, so here's the deal, and I kind of said it a moment ago. The friction force at a constant speed since it's at a constant speed, since it is at whatever, since at a constant speed, the friction force will be equal to the pulling force. Or another way to say it is this. It's even better. The net force will equal the friction force, which is negative. Or I could put either force in any order. We'll do the pulling force. Hey, let's do it this way. The net force is the pulling force plus, and it's going to be the negative friction force. Okay, so net force, this might be confusing to you. Like, why is he doing it this way? I'll show you in a minute what you can write, if you want to skip this part. All right, the net force is the pulling force minus the friction. The net force is 0. Since it's going at a constant speed, net force is 0. Therefore, if 0 is the pulling force minus the friction force, then the friction force would be equal to the pulling force. Okay? Since the net force is 0, they have to be the same. All right? That ought to make sense. Why did I write all that down? I made you write it down, but oh well. I just wanted to show you in terms of a net force equation, because you're going to see this at a later point. Oh well. Since you're at a constant speed. So what that means is friction force equals, well, if you wrote all down what I showed you, equals negative of the pulling force equals negative 59. There it is. Okay. So negative 59 newtons is the friction force. And then the last problem, C. What is mu K? Well, since friction force is a normal force, is mu K times the normal force, I left off that, then the friction force would equal negative 59 must equal to, oh, and by the way, friction, the coefficient can't be negative, so we're just going to put 59 in a minute, but the friction force 59 is equal to mu K times the normal force 118. So divide both by 118, and 59 divided by 118 is 0.5. Wow, that's a high friction. 0.50 is equal to mu K, or higher than the other one was. I usually see smaller numbers. Okay, so yeah, it's a lot of stuff. Just do number 1 and number 3, and let me show you one more thing if you just want a quick thing in case you want to see what can happen on one of those problems. All right, so I'll keep that up there. Let me take it off. So we said a moment ago that the normal force, I already erased it. Oh well, it won't really matter, but I'll have to do it again. I'll have to write it down. What if instead of pulling straight out horizontally, what if I pulled 59 Newton with my pull? However, what if I pulled at an angle? Like, let's make it 30 degrees. A 30-degree angle. Well, in that case, look at what's going to happen. Your friction force will not equal the pulling force, but it will equal FPX, FPY. Okay? It would equal the FPX force, not the friction force. I mean, the friction force would equal FPX, not the pulling force. So you'd have to find what FPX. So what you would do is you would have to take cosine of 30 is FPX over 59. So you'd have to solve that. That's one thing I wanted to show you. Okay? I'm not going to do it here. It's going to happen in the future. You're going to see that going on. And I think there's a problem that includes that. The other thing is this. If you pull at an angle, now think about this, FPY, you're actually going to be influencing the normal force. If you pull it up at an angle, you're not going to make it weigh different. It still weighs 12 kilograms, but you're lifting, FPY, it goes up. You're lifting up the weight, the block a little bit. You're lifting the rock above. That means it's not going to be hitting the surface as much. That means the normal force will be lower. Okay? So what you'd have to do is you'd have to find FPY. So I better find that one. It'll be sine of 30 equals FPY over 59. newtons. So sine of 30.5, should have known that one, right, is FPY over 59. So 29.5 is FPY. So FPY is going to be up that way, 29.1. Well, what was F weight? I forgot what it was, but it was 12 times 9.81. It was 118. F weight was negative 118 newtons. So F weight, negative 118 newtons. FPY is lifting up positive 29.5 newtons. So that means your normal force is going to be different now. You can actually say, now I've got a net force. In this direction, I got to make a net force equation. So you'd say the normal force, all of these should be equal 0. Net force equals we'll say F normal plus F weight plus F PY. So there is 0 net force. It's not moving up or down. So the normal force would be, we're trying to find that out. The weight force is negative 118, and the FPY is positive 29.5. So anyway, if I move that to that side, negative normal force equals 118 negative plus 29.5 equals 88.5. Well, we'll put 88.5. So now the normal force will be 88.5. So, of course, you could just do this. You could just say, well, if the weight pulls down 118, but because of this angle, you're lifting at 29.5, so I can just say 118 minus 29.5 is 88.5. It changes the normal force. Okay, this one gets a little bit tougher. So if you can do number 1 and number 3, wow, that is going to be great. And you can jump if you want to try to do number 4, but this is plenty for now. All right, and we'll do static next time. See you guys.